So there is no exact pathway to do this, but we'll go through several ideas of how the time scales of predictions, the processes that are important, the models that are involved, and the prediction abilities or predictability itself and how that is exploited in these models. Okay, so this is just a quick schematic from this paper about physical processes of importance to weather prediction. The paper actually talks about how weather prediction has evolved over time, and this figure is from the same paper. So you can think of here all these processes that are not necessarily represented in a numerical weather prediction model, what is typically referred to in the business as NWP. And we will see what that means and how it is done and how it is different from climate as we go along. So non-orographic wave drag, if you don't know what that is, don't worry about it. When there are waves in the system and they bend and fold, you can imagine that there is going to be some kind of a friction between different layers of the system. Of course, there are cloud processes which are not completely represented from first principles, like the energy equation, momentum equation, thermodynamic equation, continuity equation, and so on. You don't have a full-blown equation for cloud which goes from molecular scale to these synoptic scales. And there are various types of convection: deep convection, which has different kinds of processes than shallow convection. The rainfall processes are always difficult to represent. There is, of course, the basic energy balance of a short wave coming in being reflected by the albedo, including cloud properties, land properties, and so on, and long wave or infrared energy that has to go back, and how that gets absorbed in various components of the atmosphere, ocean, and land. And there are fluxes between the ocean and atmosphere, land, and atmosphere, and so on: sensible heat flux, turbulent diffusive processes, subgrid scale, orographic drag. Subgrid scale here quickly means that the numerical weather prediction and other climate prediction models take the sphere, Earth and ocean and atmosphere and land, and represent them into what are called grids. So you numerically, discretely represent the system, and the processes are represented at grid scale. All the variables like temperature, humidity, winds, etc., and in the ocean, currents and temperatures, salinity, and so on. And processes that are not explicitly represented are called subgrid scale processes. We will hopefully learn as we go along. And then there are chemistry, which are going to affect energy balance and other things, right? So in the numerical weather prediction model, not everything is represented. As we will go on, we will see that since numerical weather prediction is done on a time scale of a few days, you can assume that the ocean, which has high heat capacity, is just sitting there, and it can be assumed to remain constant through this time. This thinking is evolving already, but anyway, to start with. And there are numerical and technical ways and other data-based ways in which predictions can still be improved. One of them is called the Ensemble Prediction, where you take initial condition when you want to make weather prediction. Let's say the ocean is prescribed, and let's say some parts of the land are prescribed. Atmospheric composition like ozone and methane and aerosols are prescribed. The initial conditions in temperature, humidity, winds, etc. will have to be prescribed for integrating forward for 1 hour, 2 hour, few hours, days, and so on. And that initial condition can be perturbed in various physical ways. and different realizations of the forecast are then made. Okay, so you can see here the slight deviation in the initial condition within this range of uncertainty produces multiple realizations of the prediction after a few days, which is called forecast uncertainty. Okay, so why do we do this? Basically because Mother Nature is integrating forward and giving us one realization. Let's say this one is the reality, which is not here, but I'm just saying. But Mother Nature could have gone in multiple directions as well, based on slight differences in the initial conditions. So you try to capture the range of realizations Mother Nature could have taken, and hope and expect that your system is able to envelop the realization that Mother Nature achieves each time. So here this is like a ensemble mean. So you make multiple realizations and look at the mean and put some probability around it, and let's say you say 30% probability of rain over London or over Mumbai and so on. Okay, this now is extended to not only do perturbations of a single model, but also include multiple models in what is called multi-model ensemble. And there are reasons why when we do this the forecast skill improves. A lot of the internal variability or internal noise of the system tends to get smoothed out, and the signal to noise ratio improves. Lots of technical words, but just hang with it and then look up separately, or we will learn more of these things as we go along. Okay, so this is a way of improving predictions with the limitations of representation of processes and the lack of coupling between the atmosphere and the ocean and lack of explicit evolution of things like atmospheric chemistry when the integration for weather prediction are being made. So this is the way to look at it as a phase diagram in terms of model complexity. So flow simulation to fully coupled Earth system, and going at scales of 10 to the minus 2 kilometers, so order meters, to planetary scales 10 to the 4 kilometers, with processes ranging from turbulence, convection, storms, tropical cyclones, fronts, subseasonals to seasonal teleconnections, and interannual variability and longer, which we won't get into here because this is more about subseasonal to seasonal. And to do things at very high resolution here, this is model resolution. If you have lots of grids, for example, on the sphere, you're going to have lots of computations. The computing power you need are going to be very high. So you're going to make some compromises based on the computing limitations. And there are also ways to initialize the system by blending the data with the models, not only in the beginning, but along the way as you're integrating, let's say, every 6 hours during the forecast and so on. And those assimilation, available observations and their assimilation into the system to do better forecasts of some processes is also something model complexity has to worry about. And then there is coupling of the ocean and the atmosphere, and maybe chemistry and land and various details of vegetation and so on, which are going to continuously add computational costs and slow down. So think of making a forecast for 6 hours. The forecast has to be done well before 6 hours. If the integration takes longer than 6 hours, then you're not going to make forecasts in time. This is what happened when Charney started in the 1950s. Amazing seminal work, but the integration took, I think, a 24-hour forecast took 36 hours to integrate. So computational power decides that, details of the model decides that, model complexity, coupling the processes, and so on. So processes that are not explicitly represented are often parameterized, like clouds. If we don't represent the first principles of clouds, then you use some other variables of the models like vertical motion, saturation, vapor pressure, etc. to say form clouds. And then to rain, again, you need certain parameterizations. So those are empirical representations of the processes. And throughout the system you have errors or biases that arise from lack of representation of processes, and process understanding missing, and so on and so forth. Okay, so those are the processes and timescales and resolutions, and how the forecasts happen, how models are differing in complexities, and so on. So we'll see some more details as we go along.